hypothesis testing for the mean is where we're going to start. So this is to test claims about a population mean. And as mentioned in the introduction to hypothesis testing, we will use sample data and see how the results of our sample stack up against the claim. Now, like with confidence intervals, we have two different distributions that can be used depending on whether the value of sigma, the population standard deviation, is known or not. Now, as we saw, the vast majority of the time, you never actually know the population standard deviation. You can assume it to be a certain value, but you never actually know for sure. So instead, we're going to use the student t distribution. So remember that the student t distribution is a bell-shaped curve, just like the normal distribution. It is symmetric about its mean, but its shape is determined by the degrees of freedom. The degrees of freedom is always one less than the sample size. The idea being that the larger the sample is, the more this aligns to the normal distribution, to a point where if the sample size is large enough, it has virtually the same shape and virtually the same critical values and the same shape, areas underneath its curve that the normal distribution has. Now, the test statistic, because again, the t-distribution is much like the standard normal curve where everything would have to be converted to a z-score. In this case, everything needs to be converted to a t-score. The test statistic to convert a sample mean into a t-score starts with the difference between the sample mean that we get and the claimed population mean, and that is divided by the standard deviation, the sample standard deviation, over the square root of the sample size. This is the test statistic that we will use in performing our hypothesis tests. Now, the general procedure for a hypothesis test, to recap all the different things that were talked about in the introduction to hypothesis testing, we need to start with a claim. There is a claim that is given in the problem, and it is up to us to identify it and to write it as an equation or inequality, depending on the nature of it. If the claim is that the mean is a certain value, then we would write mu equals that value. Or perhaps we're given a statement that the mean is less than or greater than a certain value. Now, the claim may be either the null or alternative hypothesis, but either way, we need to identify both of those things. So once we have the claim, we can figure out whether it is the null hypothesis or the alternative hypothesis based on whether it includes a statement of equality. The null hypothesis always includes a statement of equality, whereas the alternative hypothesis will be strictly less than, greater than, or not equal to. But whichever one the claim is, we need the other. Now, along with that, we will be told the level of significance. So we need to pick that out of the problem. It's usually quite obvious. It'll say test it at the 0.05 or the 0.01 significance level. So that tends to be pretty obvious to pick out. Now, we need to then calculate the test statistic. So a sample will be drawn, and that sample will have its mean and standard deviation or what have you. And we need to calculate the test statistic from that information. We also need to know whether the test is going to be a left tail, a right tail, or a two-tail test. Remember, that can be identified based on the symbol used in the alternative hypothesis. If the alternative hypothesis is a less than, then we are doing a left tail test. If the alternative hypothesis is a greater than statement, it is a right tail test. And if it is a not equal to statement, then we're doing a two-tail test. From there, we can either use the p-value method or the rejection region method. The rejection region method is also sometimes called the critical value method to make a decision about the null hypothesis. Remember that the test is always done on the null hypothesis, regardless of whether the claim is the null or the alternative. We always test the null hypothesis. And then once we make that decision, we can write the conclusion statement. So we're going to look at an example, and we're going to do both the p-value and the rejection region method on it, but we're going to go through this entire procedure. So let's take a look at an example here. Suppose an agency claims that the mean radiation emissions of cell phones is less than 1. The unit here is watts per kilogram. So, the unit notwithstanding, the mean radiation emissions is claimed to be less than 1. A sample of 11 cell phones of various brands is found to have a mean of 0.938 with a standard deviation of 0.423. So we're going to use that sample data, or those sample statistics, to test the claim about the population mean at the 0.05 significance level. So the first step is to identify the claim. The claim is that the mean is less than 1.00. Because this does not include equality, this is strictly less than, this is the alternative hypothesis, H sub A. Therefore, the null hypothesis would be that the mean is greater than or equal to 1.00. Remember, these have to be completely contradictory statements. The null hypothesis has to include a statement of equality. Now, that being said, the null hypothesis can simply be mu equals 1 or mu greater than or equal to 1, either way. But certainly, the claim that the claim is given that the mean is less than 1. That is certainly the alternative hypothesis. And we are also given the significance level, so let's jot that down. Alpha is 0.05. Remember, alpha, the significance level, is the probability of making a type 1 error. The type 1 error is where we reject a null hypothesis that is objectively true. And we want to typically have that be a small probability. So values like 0.05 or 0.01 are typical. So we are also given that the sample mean is 0.938. The sample standard deviation is 0.423 with a sample size of 11. These three values together can be used to give us the test statistic. Our test statistic, again, we're going to need a t-distribution because we do not know the population standard deviation. And we are working with a small sample on top of that. Our test statistic is x bar minus the claimed mean over s divided by the square root of n. So 0.938 minus 1 over 0.423 divided by the square root of 11. Of course, numbers like this are why calculators are our friend. What we get out of this is a t-value of negative 0.486. Now, what does that actually mean? Well, now we've reached the point, we have one more step here. We need to determine if this is a left tail, a right tail, or a two-tail test. So we use the alternative hypothesis for that. Specifically, we're going to look at what is the symbol. Oh, excuse me, I didn't mean to do that. I meant to do that. We're going to look at what is the symbol used. A less than symbol means that we're looking at a left tail test. So we have two ways we can go about looking at this. The first that we're going to look at is called the rejection region method, or the critical value method. It's the idea that the value of alpha is going to determine what a critical value that tells us if our test statistic is varying from the mean, the claimed mean, too much. So the idea is that there is a value out here that has an area to the left of 0.05. Remember, this is a left tail test. So we want all of that 0.05 area in the left tail. The question is then, what is this value? That is our t sub alpha. Now, the way that we're going to get the t sub alpha value is we're going to go to our calculator and we're going to use the inverse t command. The inverse t command needs the area to the left. As its first parameter, and then it needs the degrees of freedom as its second parameter. So in this case, t sub alpha is going to be 0.05, or I'm sorry, inverse t, excuse me, I forgot the inverse t command. Inverse t of 0.05, comma 10. Remember, our sample size is 11, which means our degrees of freedom is 10. And that's going to give us a t sub alpha value of negative 1.812. What we can do now is compare the t value from our test statistic to the t-value of our critical t-value. The idea being that a t-value of 0 is right in the middle and would be if we had a test statistic that is exactly equal to our claimed mean. So a t-value of negative 0.486 would be about here. This is where our sample data is. Our sample data showed a value fairly close to the claimed mean. The idea is that something would have to be very, very far off to the left very, very far off to the left, inside this actual red region down here. That red region is known as the rejection region. Our test statistic would have to be that far away to suggest the null hypothesis is wrong. Now, what we did get was something that was indeed smaller than the claim, because we got a test statistic that was negative 0.486. So we definitely got a test statistic smaller than the claimed mean. The question is, was it small enough to suggest the null hypothesis was wrong? And the answer is no. Since our test statistic is not within the rejection region, we do not reject the null hypothesis. That is how the rejection region works. The rejection region works by establishing the critical value that says this is the point where you need to be at to reject the null hypothesis. You need something that is significantly varying from the null hypothesis's claim, or from what the null hypothesis is saying. You need something that varies significantly from it to say that the null hypothesis might just be wrong. Anything that doesn't go out that far is not strong enough evidence to reject the null hypothesis. So we do not reject the null. By extension, that means if we are not rejecting the null, we must be rejecting the alternative hypothesis. We'll come back to writing our conclusion statement in a few moments. I now want to look at the p-value method. So the p-value method is going to take our test statistic, negative 0.486, and find the probability of having a more extreme result than this. That is to say, we're going to take our value of negative 0.486 and we're going to ask ourselves, what's the probability or the area further out than that? The area of this is our p-value. Now, how do we find that area? Rather than an inverse t command, remember, an inverse t is meant, like an inverse normal, is meant for when you have the area and you're looking for the t-score or the z-score. In this case, we have the t-score. We're looking for the area. So what we need here is our tcdf command. The tcdf command, much like the normal CDF command, needs a lower or left bound an upper or right bound, and it's going to, of course, need to know the degrees of freedom. So for us, we need our tcdf command to use negative infinity, or our version of it, and for the right bound, negative 0.486, with the degrees of freedom being 10, again, 1 less than the sample size. And this gives us an area of 0.3187, etc. That's the area of this blue region. That's a pretty significant area. In fact, the more area it has to the right, or the more area it has to one side of it, the less extreme our test statistic is. So if we have a larger p-value, the less extreme the test statistic is. And remember, what we're looking for is an extreme test statistic that will suggest the null hypothesis should be rejected. A less extreme test statistic suggests the null hypothesis may be correct, or at least we don't have enough evidence to say it's incorrect. Conversely, or I should say contrapositively, what we should say is that the smaller the area, the more extreme the test statistic is. So, oh, excuse me, I don't know what I was writing there. Either way, whether we're using p-value or rejection region, what we're ultimately looking for is to say how extreme is our sample data. Is it so extreme as to suggest the null hypothesis is wrong? Or is it not very extreme and therefore the null hypothesis is supported, or at least it's not strong enough to say the null hypothesis is wrong? So in either case, whether we're using the rejection region method or whether we're using the the p-value method, we're looking for the level of extremeness of our sample. And if it's not extreme enough, then we fail to reject the null hypothesis. This is a pretty mild test statistic. It is not that extreme. By comparison, remember, by comparison, a value of, was it negative 1.812, has an area to the left of 0.05. So you can see how a more extreme value has less area to its, to the outside of it. So what we're seeing here is that our test statistic is not as extreme as our critical value, and therefore we should not be rejecting H sub O, our null hypothesis. So whichever method is used, that's all it's about, is saying how extreme is our test statistic. Is it extreme enough to reject the null hypothesis? Or is it not that extreme and therefore we fail to reject the null hypothesis? Now, what are the benefits of each? I personally like the rejection region in the sense that it defines if you're over here, it's definitely reject, and if you're not in that area, then it's fail to reject. I like how clean it is. I like how it sets, through the critical value, it sets the threshold. The p-value, on the other hand, is nice in a different way, because the p-value is the same regardless of what the level of significance is. And that's where the rejection region kind of fails a little bit. Or not fails, but becomes more cumbersome. The critical value of the rejection region is based on the level of significance. If we change the level of significance, we have to change the critical value. The nice thing is the p-value is always based off the test statistic. So regardless of the level of significance, the p-value in this problem is 0.3187. That allows us to change the level of significance and not have to redo any of the work. So the p-value method is better for comparing to different levels of significance. The rejection region, I think, is nicer for making a very clear cut, here's where you reject, here's where you don't reject. And I think for students who are just learning this, the rejection region is easier to understand and easier to work with. But that being said, having to find the critical values using the inverse t command, which not all calculators have, if your calculator doesn't have that inverse t command, then you're going to have to use the t-table like we used for the confidence intervals when we had to use the t-distribution. So maybe not the greatest idea in the world, but that being said, if you have it on your calculator, then the rejection region method is not that big of a deal. The p-value method is something that all of you should be able to do because all of your calculators have the tcdf command. So you can all do the p-value method. And again, once you're comfortable enough with the nature of hypothesis tests, the p-value method, again, makes for a much quicker and cleaner way to compare to different levels of significance. Now, in this case, we got a test statistic 0.3187 that was quite large. There isn't a level of significance out there that's going to change our decision here. But sometimes your p-value is very, very close to your alpha value, and a slight change in your alpha value, a slight change in that level of significance, could change your decision. The p-value method makes for a quick comparison to the level of significance without having to recalculate anything. So it definitely has its advantage there. So let's move on to the conclusion statement here. So we have h sub a was that mu is less than 1.00, and that was our claim. We have our null hypothesis then, which is that mu is greater than or equal to 1. And whether we use the rejection region or the p-value, the decision made was that we fail to reject the null hypothesis. We fail to reject the null hypothesis. So our conclusion statement then, remember, it has a few options in it. We're going to say there is or is not, depending on what our decision was. Our decision to fail to reject h sub o means we're going to use the word is in our statement. And because the claim was the null hypothesis, was the alternative hypothesis, we're going to use the word support. So our conclusion statement is going to say there is enough evidence I said that entirely wrong. Is not. If our decision is to fail to reject the null hypothesis, then we're saying is not. Okay, that makes more sense. It wasn't quite working in my head there for a second. there is not enough evidence to support the claim. Now, again, it makes more sense when once you've written it, to go back and look at the problem and look at the claim that was made and the decision that was made. So the claim was that mu was less than 1.00. Our sample data came up with a mean of 0.938. Now that was smaller than 1. But the question here is, was it smaller enough? It's pretty close to 1. In order to support the claim, it has to be definitively less than 1. They claim it's less than 1. We need something that is definitively less than 1. What we got was something that was smaller than 1, yes, but not small enough. If we had gotten something that was like, say, 0.75, well, that's distinctly less than 1. Or if our sample mean came out to be 0.21, that is significantly less than 1. 0.938 is actually pretty close to 1. So it's not saying that the mean radiation emission isn't less than 1. It's saying that the evidence in our sample wasn't enough to support that claim. Now, what we could do is we could go out and get another sample, a bigger sample even. But considering the size of our sample and considering how relatively little it deviated from the claim of 1 or less than 1, it wasn't significant enough. It's not saying that the claim is wrong. It's just saying our evidence wasn't strong enough to say, yes, this claim is true. So we don't have enough evidence to say the claim is true. We gotta go with the null hypothesis for the time being. Again, we could go out and get another sample, a bigger sample, and maybe that bigger sample would be enough evidence to support it. But the sample we got was not strong enough evidence. And that's the nature of the conclusion statement. It's not that our sample didn't match what the claim was, it's that it wasn't a strong enough evidence. It would be like saying, oh, I flipped a coin twice and both times came up heads. I guess that means that this coin is always going to come up heads because 2 out of 2 flips were heads. Well, it's not strong enough evidence because you only flipped that coin twice. Now, if you flipped it 100 times and all 100 times came up heads, well, that would be much stronger evidence for the claim that, hey, this coin always comes up heads. So it's a matter of the strength of the evidence, not just whether the sample matched just on its surface what the claim says, it's whether the evidence is strong enough. And here the evidence wasn't quite enough. Doesn't mean the claim is wrong, just means our evidence didn't support it. So that's the basics, a basic example of hypothesis testing. But there is, again, on the first bit of this lesson, we had a generalized procedure, and there's a Word file on the course website that has a more fleshed out version of that general procedure. So between those two, we can start doing our hypothesis tests for the mean.